All right, here we go. So, on Monday, we made it through November. So this is starting with December. And so this topic was what we did a little bit before we went home for Thanksgiving. We did a little bit of stoichiometry, but a lot of this was while you guys were at home in December. Well, you guys have always been at home. So you were online then anyway. But all right, stoichiometry is basically looking at periodic or chemical reactions and viewing them as a recipe and being able to use the information you have to figure out how much you're going to produce or how much you would need. It's basically reading a recipe and converting recipe ingredients. Okay. First of all, you've got to be able to balance equations. There are a ton of practices out there, practice sites where you can balance equations on. Just Google it and you can find them. Go on, balance to practice. The only way you're going to ever conquer balancing equations, if you're not comfortable with it already, is to practice. Okay. I can't remember if there's a question on. I think there is a balance, and I think it's a combustion question. Let's see. Yes, there's one combustion reaction that you have to balance. So let's talk about the reaction types real fast. What do we call a reaction that makes one product? What kind of reaction is that? You can holler it out in the chat to everybody if you want to. Oops. I don't think I shared this the way I like to share it. Hang on. I didn't. I'm sharing the whole screen anyway, but I like to have that. All right. Anybody come up with what one product is? This is synthesis. I'm going to write smaller because I feel like I'm really zoomed in right now. And I'm going to change that pen. Okay. So A plus B is a synthesis reaction. A decomposition reaction is when you have a compound that breaks into smaller compounds or elements. A single replacement is when an element replaces another element in a compound. And a double replacement is when you have two ionic compounds switching places. These are solubility problems. The last one is combustion. What happens in combustion? Don't be shy. Somebody shout it out. sure my sound is turned up so I can hear you all. All right, Dinosaur Sue, what is combustion? Combustion is when you have a hydrocarbon, which means you have some type of carbon and hydrogen and maybe an oxygen that reacts with oxygen to form carbon dioxide and water, okay? That is a combustion reaction. That is what makes fire. That is what makes energy for our bodies, okay? You all have little fires going on in your bodies right now because you are all making carbon dioxide and water. Okay, so there is a balancing equation for combustion on the final. So that's something you definitely need to know. All right, back to stoichiometry. Stoichiometry is simply, come on, let's make him a little smaller since we're writing smaller today. Stoichiometry is simply being able to change from one substance to another. And I use a bridge analogy. You have to change, you can only change from moles to moles. You can't go grams to grams without going through moles first, because all atoms have different masses, but we count them the same. And mole is a number, so it's being counted as opposed to being measured with a balance, all right? So if you are doing stoichiometry, you figure out, read the problem. For instance, if we have, we'll just use this. Methane burning. Methane plus oxygen gives us carbon dioxide and water. If we have methane burning, for every one methane, because this is a 1 in front of it, we're going to need 2 oxygens. So if I'm using my, if I give you this problem, I have 10 moles of methane. How much oxygen will I need? So now I'm going to go over here. My known is methane, and I have 10 moles. How many moles of oxygen will you need? Well, to me, this is quite simple because I've done this for a long time. But I know that 1 mole, 10 is to 1, as the unknown amount will be to 2. So I can set up a cross multiplication here. And if I do that, I'm going to take 10 moles of CH4 times 2 moles of oxygen over 1 mole of CH4. That right there is our mole ratio. And that is what is going on in the middle of the mole bridge. This is our mole ratio. So if you can look at a problem and go through and figure out what do you know, what information is given to you, that you know lots of information about one of the elements or compounds, you can convert to the other. And it's basically what you're doing is you're going to take the known mole, 10 moles of methane. We know that 1 mole of methane reacts with 2 moles of oxygen. So that tells us we would need 20 moles of oxygen. Okay. Moles are easy. What if I give you grams? What if I tell you instead of 10 moles of methane that I have 10 grams of methane? And I want to know how many grams of oxygen that's going to be. Well, the first thing I have to do is change to moles. So what we do, and the reason I use a bridge, is if we're starting in grams, how do I change from grams to moles? Look at a mole map if you need to. Mrs. Bush, you divide by the molar mass. Thank you, Sue. Okay. Then you go through the mole ratio. And if you want to change back to grams on the other side, Sue, you multiply by the molar mass. You're a smart dinosaur, Sue. Okay, so we would take 10 grams. The molar mass of methane is 16. There is one methane molecule that is needed for every 2 moles of oxygen. And the molar mass of oxygen is 32 grams because there's 2 oxygens, each one 16. And that would be how we calculate that. Okay. Another thing that we learned this year was numbers and using Avogadro's number. So if I know a total number of particles, for instance, let's say that I tell you that I have 1.8 times 10 to the 21st molecules of CH4. And I want to know how many molecules of oxygen I'm going to need. So first, I'm going to take particles, and I'm going to divide by Avogadro's number. That changes me to moles. And then if I want to go back to particles, I multiply by Avogadro's number. Okay? So I would do 1.8 times 10 to the 21st. We have a 1 mole. Oh, no, we have to divide by molar mass. I mean, Avogadro. 6.02 times 10 to the 23rd. Molecules in 1 mole. 1 mole of CH4, 2 moles of oxygen, and then we would multiply back 2 times 10 to the 23rd. Some of you may notice that there's an extra step in there. We actually could have just gone straight because molecules and moles are both a number. We don't actually have to change it to moles, but let's not worry about that right now. 2 molecules in 1 mole. And that would give us our answer. Okay. Questions about that? I'm gonna come back to this. We're not done filling this in. Okay. We're gonna come back when we get to molarity and when we get to gases. So hold that thought. All right, let us go on and talk about what do you do when you're finding limiting. Limiting means you have to determine what will be used up first. What, I should say, what reactant all right, so for limiting, we'll use the same equation. Let's say I tell you I have 10 grams of methane, and I have 20 grams of oxygen, and I want to know how much CO2 will I theoretically get. How much CO2 will I get? Theoretically means what should I get? So the way that I taught you guys is, and I guess I should be writing this under limiting reactants. Let me bring this up. There we go. So what you do, take 10 grams of CH4, change it to moles. Calculator. 0.625 moles. Do the same thing. 20 grams of oxygen. Okay, that's weird. Oh, it's because oxygen's 32 and methane's 16. Okay, so we would have that amount of moles of methane available and oxygen available, okay? What we want to do is figure out which is going to make more carbon dioxide. And you could go on and calculate carbon dioxide using stoichiometry, but there is a shortcut that I taught you. And that shortcut is next, you look at moles divided by the coefficient, and the smaller one is what's limiting. So I can divide him by 1 because there's a 1 in front of that, and I can divide him by 2. Who's going to be smaller? The oxygen is going to be smaller, so therefore oxygen is limiting. I then use oxygen to do the rest of my calculations. So I had 20 moles or 20 grams of oxygen divided by 32 grams in 1 mole. And then my mole ratio, 1 mole of methane reacts with 2 moles of oxygen. And then if I want to know grams, no, not oxygen, carbon dioxide, that's what I'm solving for, right? So it's a 1-to-1 ratio. 1 mole of methane reacts with 1 mole of CO2, and the molar mass of carbon dioxide is 44 grams in 1 mole. And that's how you would do that. Okay. Percent yield, you're just simply going to figure out what percent you actually got. All right. So for percent yield, you're going to take the actual amount that is measured in lab divided by the theoretical amount times 100. So let's finish this problem with the methane and the carbon dioxide. I used the wrong one. This should be 2 moles of oxygen to 1 mole of carbon dioxide. All right, 20 divided by 32 divided by 2 times 44. 13.75 grams of CO2 should be produced. This is theoretical. All right, let's say that I got 10 grams is what I actually measured. Then I'm going to take 10 grams divided by 13.75 grams times 100, 73%. Okay? So that is percent yield. All right, solutions. A solution is something where you have something dissolved in another substance. We were talking about liquid solutions. We use this when we talk about something that is dissolved. So we're talking about solution chemistry with water. All right. And what we're going to look at are the double replacement reactions. Now, what does it mean if something dissociates? I'm doing it out of order again, but that's okay. If it dissociates, that means when you put it into water, the water particles are strong enough to pull those ions apart and cause them to be floating around in the solution. Okay? So that is what we're talking about when we talk about solution. And I've got dissociation down here, so I'm just going to do it up here. And we'll do molarity next. So what did I want? Solubility. So when you're writing double replacement reactions, since those reactions are going to dissolve in the water, a molecular equation would be sodium chloride, that's dissolved in water, plus silver nitrate that's dissolved in water, will give us sodium will trade places with the silver, so sodium is now bonded to silver nitrate and silver chloride. Now, we have to figure out what is going to be soluble and what is going to be insoluble. So we'll need to look at our solubility table. Here's our solubility table. One of our products was sodium nitrate. Sodium is in group 1A. All sodium substances are soluble. Soluble means dissolve or dissociate. Okay. Insoluble means that it will precipitate or form a solid. And we use that symbol for something that is insoluble. So sodium substances are always soluble, nitrates are always soluble, so sodium nitrate will stay dissolved. But chlorides will precipitate. They're not soluble when mixed with silver. So we are going to have a solid form here. Okay? Our molecular equation Sodium chloride plus silver nitrate gives us sodium nitrate and silver chloride. All right, I got to take a quick break because I need to run to the bathroom. Sorry. I'll be right back. Sorry about that. Okay. So we're talking about equations. A molecular equation is an equation that describes what's going on. If we do a complete ionic equation, we're going to dissociate everything that can be dissociated. Okay, that's a complete ionic equation, and then a net is only the stuff that was involved, and the only thing that was involved was silver chloride to make silver chloride. Okay, so, and the way we figure out what is soluble is you have to be able to read a solubility chart. All right, so I'm going to remove that because we already talked about it. And that. So now let's talk about molarity. Molarity is concentration. That's an N. Concentration. You guys are all familiar with concentrations because you've all made powdered drinks at some point or another, and you may have added double packets of, if you have the little Kool-Aid sleeves that you can put right into the bottle of water, you may have put 2 in so that you get a more concentrated flavor. You may have diluted it at some point. Concentration basically means amount of solute that has been dissolved in a solvent. It's a ratio, solute per solvent. Of course, when we talk about amounts in chemistry, we use moles. And when we talk about solvent, we talk about volume, and we use liters. So we call this relationship molarity. And it is basically the ratio of moles per liter. Moles divided by liters. Okay? So if I tell you that you have 10 grams of sodium chloride, and I want to know what molarity, you're going to dissolve that in 0.250 liters, which is about a cup. I want to know the molarity. So for this one, you got to look at your mole map. Did we do a mole map yesterday? Yeah. Okay. We want to ultimately go to molarity, and we want to start, we're starting with mass. So the first thing we're going to do is divide by molar mass and then divide by the volume. All right. So, no, I want to go back to this. So we're going to take 10 grams divided by the molar mass of sodium chloride, which is 35.5 and 23, 58.5. That gives you moles, and then you divide by the volume. And our volume was 0.250 liters. 10 divided by 58.5 divided by 0.250 is a 0.68 molar solution. Okay. Now we can do stoichiometry with molarity. So I'm going to go back up to the stoichiometry and the mole bridge. So if you're keeping track here, so I'm going to go back to our mole bridge. Now, if somebody tells you that they have a solution that has a molarity of, let's say 0.68 molarity, and they have 250 milliliters of that. So let's say we have sodium chloride, and we're going to add silver nitrate. Okay. And let's say we want to know what amount of silver nitrate do we need to add in order to react all of the chloride. We don't want to add extra. So we're going to figure out what molarity, and we've got silver nitrate, actually let's say we know the molarity. If we know the molarity of the silver nitrate, so let's say the molarity of the silver nitrate is 100, and we want to find volume. Okay? So, start with volume, which was 0.250 liters. How do I go from volume to moles on the mole map? To go from volume to moles, I multiply by the molarity. Okay? So I'm going to go volume times molarity, 0.68 moles per liter. Now I'm at moles. Now I have to go to silver. My ratio is 1:1. So I multiply by the mole ratio. 1 mole of NaCl will react with 1 mole of silver nitrate. So now I'm across the bridge, and I need to go back, because I'm solving for volume. To change back to volume, we're going to divide by molarity. And that'll give us the volume in a liquid. All right. What if I had said, instead of, I had a 0.100 molarity of 1.100, let's say that I reacted it with 250 milliliters of silver nitrate, but I don't know what my molarity was, then I would divide by molarity, or divide by volume to go to molarity. So I'm going to put another arrow on here. Divide by volume. Okay. This works for titration reactions as well, which we haven't gotten to yet. Let's do titrations next. When you're doing a titration, you have an acid and a base, or you could have 2 ionic compounds that were dissolved in water. You could have 2 solutions. And it's the same as it's just the exact same as what we just talked about. You're going to use the molarity times the volume of your known. And then you multiply by the mole ratio. And then, depending on, that'll give you moles of unknown. If you want to know volume of unknown, you'll divide by molarity. If you want to know molarity, you'll divide by volume. All right? But it's just the same. And that's there's no questions about the titrate, the indicators or neutralization reactions or anything like that. So just, I think there's a titration question and that's it. All right, electrolytes. Electrolytes are substances that conduct electricity when dissolved. Strong electrolytes are anything that is aqueous when it's in water. It also includes the strong acids. Strong acids are hydrochloric acid, hydrogen bromide, hydrobromic acid, hydrogen iodide, I don't need a 2 there, hydroiodic acid. I should be doing AQ next to each of these. Nitric acid, sulfuric acid, and perchloric acid. And the reason they are strong electrolytes is they all dissociate. Okay? A weak electrolyte is something that dissociates a little bit. Any substance that will precipitate, so a non-soluble substance, everything will dissolve to a little bit that's ionic. But something that is written as S would be a weak electrolyte. There'll be a few ions in there, but the majority of them will be sitting at the bottom of the solution as a solid. And then weak acids. And the reason that weak acids are weak electrolytes is because they dissociate a very little bit. So if you have vinegar, for instance, and you put it into water, some of it will dissociate into hydrogen ions and acetate ions, but most of it will stay as vinegar. So if you look under a microscope at hydrochloric acid, you're going to see hydrogen ions and chloride ions. If you look under a microscope at acetic acid, you're going to see mostly acetic acid molecules. This is actually something that I just did yesterday with honors, and it has a nice example of it. All right. Oops, I didn't want to erase that. Let's put this into the notes. Okay. This is a strong acid at the top, because look at what happened. These are the acid particles, and they've all broken apart, and their hydrogens have locked onto one of the water molecules. So you have the acid plus the chloride ion swimming around in there. Okay. This guy would be an example of vinegar. So if you take vinegar, let me rewrite that down here. Notice how many of the vinegars broke up. Here's one vinegar, here's 2, 3, 4, 5, 6, 7, 8 of them are still vinegar. So you're going to have some of them that stay undissociated or ionized, and then you'll have a few that will ionize. But this is what you're going to see the most of. Okay? All right. Gas laws. We're on the home stretch. Gas laws. We looked at Charles' law, which is volume and temperature vary directly. So if you know the volume and temperature of one situation and you know one of the other pieces, you can solve using that equation. Boyle's law. Pressure and volume vary inversely. So if you know the conditions of the pressure and the volume, and then you change one of them, you can calculate the other using that equation. Gay-Lussac's law is pressure and volume. No, pressure and temperature. I lied. Okay. We can also take into consideration Avogadro's law, which is volume is related to the number of particles. More particles, your volume is going to increase. And then we can use PV equals nRT to solve for other gas problems where R is the ideal gas constant, and it is the pressure at STP times the volume of 1 mole of gas which is 22.4 liters, and times temperature at STP, so pressure at STP is 1 atmosphere times 22.4 liters divided by 1 mole times 273 Kelvin, and that value is 0.0821 liter atmospheres over moles Kelvin. Okay, gas stoichiometry. I'm going to go back up to the mole map, or the mole bridge. If we go back to our methane question, no, gas. if you are given a volume of a gas and it is at STP, standard temperature and pressure, you can divide by 22.4 liters in 1 mole. That is the molar volume of a gas at STP to get moles. If you're solving for the volume of a gas, you multiply by 22.4 liters per mole. Okay? If it's not an STP, and you know volume, you can solve for moles by doing N is equal to PV over RT. And if you're going back to volume, not at STP, volume is equal to nRT over P. Okay? The last two things that we dealt with when we talked about gases, Graham's law is the rate of effusion, which means the gas can go through tiny holes. This is why balloons go flat eventually. This is why a helium balloon can float, and then a couple days later it can be sitting on the floor. It's still inflated, but some of that helium has been able to escape through teeny tiny holes. And the rate of effusion, basically the larger the molecule, is a slower rate. And you can actually calculate it taking the rate of the first divided by the rate of the second is equal to the square root of the molar mass of the second divided by molar mass of the first. But I really think, I'm almost positive, without looking through here, that the question on the test doesn't ask you to calculate a rate, and it doesn't ask you to figure out a molar mass. All it says is which one of these four will go through the fastest, or which one of these four would go through the slowest. And the fastest would be the smallest. Smallest mass. And the slowest would be the largest mass. Last thing, partial pressures, which apparently I didn't spell correctly. Dalton's law of partial pressures. The total pressure is equal to the sum of each of the individual pressures. All right, so if you're doing something and you know the pressure of the oxygen is 1.35 atmospheres, and pressure of nitrogen maybe is 2.10 atmospheres, and the pressure of carbon dioxide is 0.55 atmospheres. To get the total pressure, you just add them all up. And that takes us up through the end of February. Anybody have any questions? All right, if there's no questions, then you guys can spend the rest of the hour working on